All right, omega 2a exponential functions. The directions for the first three problems. Use a calculator to evaluate each expression to the nearest 10,000th. There's really not much for me to say here, but put it in your calculator. This ends up being 77.5705. If you need help on how to use your calculator, please come see me. 8 to the cubed root of 3 is 33.6604. Number 3, 5 to the 10th root, 5 to the square root of 10, approximately 162.3070. These are all approximates. That's 1 through 3. Easy peasy. Number 4, graph each equation using the parent graph. Well, parent graph is an exponential function with a horizontal asymptote at y equals 0. This base is 3, so it's going to grow faster than a base that was a 2. As it goes to the right, it crosses the y-axis at 1, and then it grows faster than it would if that was a 2 as a base. As it goes to the left, it's getting closer and closer to the x-axis. That's number 4. Number 5 appears to be strange. In fact, the way it's written, it is strange. All the examples that I've shown you up to this point, the base has been an integer. This is a fraction. Well, when in doubt, make something what you're used to seeing. 1/3, if you want it to be a 3, if you want to reciprocate it, change the exponent. Right now, 1/3 actually has an exponent of 1. Because you don't see an exponent inside the parentheses, so that would be a -1. Power to a power rule, that's going to be 3 to the negative x. So how do you graph 3 to the negative x? The negative is inside the function. Therefore, it reflects over the y-axis. If you reflect a horizontal line over a vertical line, it will not change, or at least it will appear not to change. The right side becomes the left side becomes the right, yada, yada, yada. It looks the same. Your curve, then, is going to look like this. As you go right forever, it gets closer to the x-axis. As you go left, it gets tall super duper fast. That is number 5. Question 6. Compare and contrast the graphs of examples 4 and 5. Well, they are the same curve. Y equals 3 to the x is the same curve to y equals 1/3 to the x, which this, of course, is 3 to the negative x. Meaning that the two curves are congruent to each other. The exact same size, the exact same shape. They have the same y-intercept. They have the same horizontal asymptote. How are they different? How do they contrast? The second graph is reflected over the y-axis. Those two graphs are symmetric with respect to the y-axis. Say something like that, and that would give you a good answer for number 6. Number 7, we got y equals 5 to the negative x. 5 as a base is going to grow faster than 3 as a base. For example, let's say that this was y equals 3 to the x. Then this might be something like y equals 5 to the x. Bigger the base, the faster it grows. Still has the same y-intercept, though. Still y-intercept is the same, which is 1. Here is 5 to the negative x, which reflects it over the y-axis. So your horizontal asymptote doesn't appear to change, and your curve looks like this. It gets tall really fast as you go left, and it gets closer and closer to the x-axis as it goes to the right. Problem 8 is the same problem as number 5. Number 5 was y equals 1/3 to the x. Same thing. It is the parent graph of y equals 3 to the x reflected over the y-axis. Y-intercept of 1, horizontal asymptote at y equals 0. Number 9, this is y equals negative 3 to the x, which is different than y equals 3 to the negative x. This negative in front of the function reflects the graph over the x-axis. If a horizontal line is on the axis of reflection, then it doesn't change. This horizontal asymptote is still y equals 0. Our curve now is going to look like this. Instead of having a y-intercept of 1, it is at negative 1. Dunsies. Not the Dundies. Those are Michael Scott's awards. That is Dunsies. Number 10. Our base is a fraction. Let's make it not a fraction. To reciprocate the base of 1/5, just take your exponent, change its sign. So we could write this as as y equals 5, that's reciprocal of 1/5. Change the exponent to the opposite sign to the negative x. That negative x, have we done this problem? We have. It's the same as number 7, identical. The graph is reflected over the y-axis. Y-intercept of 1, horizontal asymptote at y equals 0. Number 11, we have y equals y equals 2 to the x plus 3. What does this plus 3 do to our graph? It translates the entire graph left 3. If you take a horizontal line and move it to the left, you won't notice. It will move, but you won't be able to tell. Instead of crossing the y-axis at 1, we move everything to the left. It's the point that was 0, 1 goes to the left. It's going to be negative 3, 1. We were at 0, 1. Go to the left 3. 0 minus 3 is negative 3. Didn't go up or down, so it's negative 3, 1. If you wonder what the y-intercept was, simply put 0 in for x. 0 plus 3 is 3. 2 cubed is 8. That'd make the y-intercept 8. That's 11. Number 12, two things happening here. One thing, this negative here, reflects the graph over the x-axis. This plus 3 translates the graph left 3. So our horizontal asymptote, it's going to move. We won't be able to tell. It's reflected, so it's going to look like this. Don't draw that yet. And then that is moved to the left 3. So it's going to look more like this. If it's moved to the left 3, and then we get to negative 1, when we get to negative 3, negative 1, and that would make the y-intercept negative 8. How can you tell it's negative 8? Put 0 in for x. 0 plus 3 is 3. Negative 2 to the third, negative 8. Number 13, we have a negative outside the function once again that reflects it over the x-axis. We have a minus 3 inside the function. That's going to translate right 3. Horizontal asymptote hasn't moved. And the graph goes to the right 3. It's reflected down, so it's going to look something like this, with what was the y-intercept of -1 now goes to the right 3, so it's 3, -1. If you want to know the y-intercept, put 0 in for x. 0 minus 3 is -3, and -2 to the -3 could be thought of as -1/2 to the third, which is -1/8. This y-intercept right here is -1/8. Number 14, so y is less than or equal to. So we're going to have to do some shading. We got 1/2 to the x. If you want your base to be integer, and you do, trust me, you're going to change this to y is less than or equal to 2 to the -x. Reciprocating your base changes the sign of your exponent. So that negative that you see up here reflects the graph over the y-axis. So the graph is going to look like this. Y-intercept at 1, horizontal asymptote at y is 0. It says y is less than or equal to, so it's shaded below. Number 15 is a word problem. What is the future value of an annuity? So I'm using the future value formula. It says, what's the future value? So f sub n, don't know what it is. If $1,000 is deposited into an account, so the payment is $1,000, paying 6% interest, so r as a decimal is 0.06, every 6 months for 12 years. Sorry, I had to go do something and I forget where I was. So f sub n is the future value, p is the dollars per payment, r is the interest rate. Notice it says that's every 6 months. N is the number of times it's compounded per year. If the interest rate is 6% for half a year, that means it's being compounded twice. So n is 2. And the time is 12. It says for 12 years. Plug these numbers in. P is 1,000. R is 0.06. N is 2. N is 2. Time is 12. Some things we can simplify. 2 times 12 is 24. 0.06 divided by 2 is 0.03. 0.06 divided by 2 is 0.03. 1 plus 0.03. So we can make this 1,000 times 1.03 to the 24 minus 1 divided by 0.03. We can take this 0.03 and pull it to the front, so it's 1,000 divided by 0.03. Gives me a rounded number, so I'm not going to do that. I'm just going to leave this as it is. Put this in my calculator, like so. And this gives me approximately $34,426.47. That is the future value of this $1,000 that you're depositing into your account, and it's paying 6% every 6 months for 12 years. All right, 16 is a pretty tough problem. The state of Ohio offers its lottery winners a choice of prizes with the jackpot amount paid in equal annual payments over 26 years or the present value of the annuity in one lump sum. If Mr. Arthur won $4.5 million, how much would his lump sum payment be? The interest rate used to find the present value is the yearly rate of inflation, which is 5%. Let's start with the easy part. Interest rate is 5%. Another easy part. Time in years is 26. So the question is, do you take 4.5 million? If you do, you get some money every year for 26 years. If you sum those monies up, you get 4.5 million. Your other choice is, I don't want to wait. I want all the money now. All the money is not 4.5 million. Now, let me explain. When you win the lottery, let's say 4.5 million, the state of Ohio does not have that much money waiting for you. They don't have it. They have a portion of that money, but if they were to invest it for a series of years, it would accumulate to be 4.5 million. So your choice is take the present value of that money, or take that money through interest over a period of time, would end up being 4.5 million. Confused yet? Well, just wait. I'll get you there. So P, dollars per payment, we don't know what that is here, but we can figure it out. The jackpot is $4.5 million. If you take this spread over 26 years, you get one payment a year for 26 years. If you divide that, your dollars per payment, you're going to get a check every year for $173,076.92. I rounded, I hate that, but it's the nearest cent. You're getting one payment a year, so N is 1. So put these numbers in and we can figure out what P sub N is, which is the present value. So the math is simple. The thinking to get the math to work right, not so simple. Let's plug these numbers in. P, $173,076.92. R is 5%, as a decimal is 0.05. N, you get one payment a year. To the negative NT, be negative 1 times 26 divided by 0.05 divided by 1. Simplifies a bit to $173,076.92. In our numerator, we're going to get 1.05 to the negative 26 divided by 0.05. Put this in our calculator. Bear with me. We end up getting, now I rounded here, which is a big no-no, so minus 5 points for me. This is going to come out to the following: $2,488,012.80. I'm off by 4 cents. I believe because I rounded in that case. I think the answer is supposed to be 84 cents. Here's what it means. When you win this lottery, your choice is to take $2.4 million in cash. Well, you got to pay taxes. Or to take $4.5 million spread out for 26 years. 17. The Millers are saving for their daughter's college education. If they want to add $20,000 to a college fund at the end of 5 years, how much should they deposit each month into account with an APR of 6.12%? This problem is asking, what is the future value? I'm sorry, it's not asking that. It's saying the future value is $20,000. What is the dollars per payment going to have to be to figure that out? We don't know what that is, so that's what P is. The interest rate as a decimal is 0.0612. You're going to deposit it each month, so N is 12. And they're going to do this for 5 years. The time is 5. use the future value formula. If you plug these numbers in, the future value is $20,000. Dollars per payment, we don't know. Interest rate as a decimal is 0.0612. Number of payments per year is 12. That's raised to the 12 times 5. Subtract 1 from that. On the bottom, divide your interest rate as a decimal by the number of payments a year. Certain things here reduce. Pardon me for my lack of energy. It is late, and I am tuckered. 0.0612 divided by 12. 0.0051. Add 1 to that. You get 1.0051. 12 times 5 for the exponent is 60. And our denominator, 0.0612 divided by 12 is 0.0051 again. Trying to get p by itself, so we're going to multiply both sides by the reciprocal of this monstrous fraction here. When we do that, 20,000 times 0.0051 is 102. Denominator is as good as we can get it without rounding. We don't want to round until we have to. Now we have to. We're at the end. Put that in your calculator. That ends up being dollars per payment, $285.77. They deposit that every month for 5 years. They will have earned enough money to pay $20,000 for their daughter's college education.